All right, so here we are back from break. We're working on problem 32 in the textbook. Are we ready to do this as a class? No? Okay. I can wait. Everyone's working hard, so we're waiting. We're doing problem 32 on chapter 9, or in chapter 9. All right. Let's do it. Do it together. Looks like you're still all working a little bit, but hopefully you have some idea of how to approach it, and this will just crystallize it when we look through this together. So we've got a null hypothesis that the population mean is 1,000. Fine, we'll assume that's true for now, unless we find overwhelming evidence to the contrary, in which case we'll reject it, and we'll accept the alternative hypothesis that the mean is not equal to 1,000. We do some research on our own. We sample 81 people, and we find a sample mean of 975. So it's, no, is that close to 1,000? Is it not close to 1,000? Well, it depends on how we look at it. We also have the information that the population standard deviation is 90. And to make this test, we're going to go with a 5% significance level. So if what happens in our outcome is less than 5% likely to happen, just randomly by chance, then we're going to reject the null hypothesis and assume the alternative. So if we were to put this all on the sampling distribution of the sample mean, let's assume 1,000 is the correct mean. What is the standard deviation of this sampling distribution of the sample mean? Is that actually, how do we do the parts to it? If somebody walk me through the math.
90 divided by the square root of 81.
Yep, 90 divided by the square root of the sample size, which is 81, which is 90 divided by 9, which is 10, right? All right, so 10. All right, that's going to give us the information we need to compute our test statistic for our sample mean. 975 is our sample mean. Let's find out just how many standard deviations away from the assumed mean that would be. So 975 minus 1,000 divided by 10, right? All right, equals negative 25 divided by 10 is negative 2.5. All right, so that's looking pretty significant, right? 2.5 standard deviations below the mean. Remember Michael Jordan had a z-score of 2.3, and he was pretty tall compared to everyone else. So this is someone who's really, really far, equally far, even further below the average. But actually, we didn't set up our critical values yet. Normally we do that first. I just forgot to do that. So let's find out what would be our rejection region for rejecting this null hypothesis. Now, is this a one-tailed test or a two-tailed test? One? Two. It is a two-tailed test because the null hypothesis is that the mean equals something, and we could disprove that two ways. It could be either really high or it could be really low. So this is a two-tailed test. And I think that's the way to look at it. We could disprove that two ways. It could be really high or really low. If it were a one-tailed test, we could only disprove it in one tail, so to speak. All right, so it's going to be a two-tailed test. We're going to have two rejection regions, one really low, one really high. If our significance level is 5%, all right, then we're looking for 2.5% in the bottom, 2.5% in the top is our rejection region. What then is going to be our critical Z value? 1.96. So 1.96 will separate the top 2.5% of the data from the bottom 97.5% of the data. Negative 1.96 will separate the bottom 2.5% of the data from the top 97.5% of the data. So our critical values are going to be plus minus 1.96. And what did we get for our z-stat? Negative 2.5. So what is our decision? So our z-stat landed right here. Negative, oh wait, no, not here. Other side, sorry. Landed over here, negative 2.5. Z-stat. Z-stat. So what's our reject, fail to reject, accept? What do we do? Reject. We reject the null hypothesis. We have overwhelming evidence to the contrary. The last thing we need to do to solve the requirements of this problem is calculate a p-value. Remember, our significance level tells us our threshold for what we consider unlikely. Our p-value tells us the exact calculation for how unlikely this particular sample would be given that the null hypothesis is true. So, how do we calculate our p-value? Well, we look at negative 2.5 and figure out how likely it would be to get a point of data that extreme. And what do we get when we see area under the curve of negative 2.5? How much? 0.0060. Okay, so that's 1/6. No, yeah, 0.6 of 1%. Yeah. So a little bit less than 1%. Now, is this our answer? Multiply by Q. Because when we started this problem, all we said was the alternative is that it is not equal to whatever you say it is. So we could prove that with a really high number or a really low number. So we need to say the chances of ending up with a test statistic this extreme is double whatever we get in that tail, which is going to be 0.0 1, 2, or 1.2%. Hopefully that matches the answer in the back of the book. Or the answer, did anyone get that answer? No. I'll just assume it's okay. Fingers crossed. Questions on that? All right, I think I want to move on and do one more question just like this. Just have you work it out, and then we'll do it as a class. So if any questions come up as you're processing the next step, I can help you with that. But if you're feeling good with this, why don't you move on to another problem, which we will do as a class. I would like to do number 6 in chapter 9. It would be page 322, number 6. Page 322, number 6. Question? No. Number 6. 322, number 6. Okay, so we wanted to know how likely it would be to get a test statistic of negative 2.5. We know that's in a very extreme edge of the normal distribution. We also know that it's less than 2.5% likely. But that's all we know right now. So we want to know exactly how unlikely it is. So we say, what negative 2.5 is the z-value that separates the bottom what percentage of the data from all the rest. The same way we say negative 1.96 separates the bottom 2.5% from the top 97.5. That's the same question. If we were to put 2.5, what would that be? Well, it would be the bottom 0.6 of 1% of data and the top 99.4% of data. Because it's a two-tailed test, we now need to double that 0.6 of 1%. Because we didn't know it was going to be really low when we started this experiment. It could have been really low, it could have been really high. So for two-tailed test, we double that. Does that make sense?
question?
It is page 568. Yes, Scott. Is that your Z-stat? Negative Z-stat? Remember, negative 2.5 is crazy extreme. Negative 87 it's off the chart. Yes, sir.
So you can kind of confuse getting this value other than checking this table variable.
You got the Z-stat? Oh wait a minute. No, we're just doing the critical values. Yeah. Okay. Yeah, that's fine.
How should I check this?
So you want 1%. So it's 2 data tests, and you want 1% of the data to roll half of the percent of the data. So you're looking for one. No, you're looking here for 1/2 of 1% of the data. So that would be 99.5. Yeah. So it'd be like right here, wouldn't it? Yeah, that's it. That's 2.58. Well, here, circle that, so you can see, like you see here, see, yeah, circle those two, this one and this one, just kind of circle that. On the other one. Okay, so that's the area you're looking for. That separates the bottom 0.5% of the data from everything else, and if you were to use the negative, or the positive would be the top 0.5% of the data from everywhere else. So you're comfortable with that part? Wait, and why it's 2.5? It's 2.58.
I also found that you mistake my interest in the reason. I know it's just the same thing. The value is getting right.
Okay. Good. We can talk after class.
Sure.
Yeah, absolutely.
Hopefully you'll understand a little bit more when we do that. All right, we ready to do this one? All right, good. So we have a null hypothesis that the mean is less than or equal to 2,000. Our alternative hypothesis is that the mean is greater than 2,000. So we're going to take some samples of size 100. We're going to get our sample mean. And we know if we were to put that sample mean on the sampling distribution of sample mean, we know it would be normally distributed, and we can say all sorts of great things as a result of that. So, is this a one-tailed test or a two-tailed test? It's a one-tailed test. If we get a sample mean greater than 2,000, then we're like, okay, doesn't matter how much greater than 2,000 it is. We could get a sample mean of like 3,000. All right, and we would not be able to disprove this because all the null hypothesis is saying is that it's greater than 2,000. So we get anything above 2,000, we don't even need to calculate, we don't even need to worry. There's only one tail in which we would be able to reject the null hypothesis, and it would be this bottom tail. It would be a number less than 2,000 for our sample mean and significantly less. Significantly less that it contained only 1% of the data. And it's not a two-tailed test. We were just calculating two tails, right? Sorry about that. All right, so this is a one-tailed test. So it's going to be a little bit different. All right, so we're just looking for the critical value. This is 1% rejection region, and what is that z value? How much? Negative, right? 2.33. Okay. So negative 2.33. If we get a test significant less than negative 2.33, we reject the null hypothesis. So let's get that test statistic. What is the question, Laura?
Why is it negative?
Because we're only interested in the negative side of the tail. So let me, if we look at this in terms of z's, this 2,000, the number would not be negative, but the z would be negative. So if we standardize, the z table standardizes everything. So it looks at the mean, whatever it is, and says, well, let's call that mean, give that mean a z-score of 0. And we're looking for anything 2.33 standard deviations or more below the mean. And the reason why it's negative is because what we would potentially be trying to disprove is that the mean is greater than 2,000, and the way we disprove that is finding a mean significantly less than 2,000. I feel like I said an awful lot of words to answer that question. I hope it wasn't confusing. Does that make sense, Lauren? All right, can someone please explain why we're only interested in the negative z-score to the rest of the class and myself and Lauren?
It's only one tail problem.
What's that?
One tail problem.
Yeah, it's a one-tailed problem. Can you elaborate a little bit more?
We don't have to worry about if it's greater than 2,000.
Yeah, we don't care if it's greater than 2,000. We're looking for a test statistic that's negative and significantly negative. That's the only thing that's going to be relevant to us. All right, so let's find that test statistic. We have a sample mean of 1955. We know the population, standard deviation of 150. So let's find our standard deviation of sampling distribution of sample mean is 150 divided by the square root of n, which is 100. So that's 150 divided by 10. 15. Excellent. So our z stat is going to be the difference between our sample mean and the assumed sample mean. So 1955 minus 2,000 divided by 15. All right, equals what?
Minus 3.
Negative 3, exactly? All right, fantastic. So that's negative. What? Negative. It is 55. 1955. So what is this on the top? That's negative 45. Yes. Okay. 15 goes into 3. 45. 15 goes into 45 3 times. Sorry about that. Okay. So it is negative 3. All right. Here's where our z-stat lands. Z-stat is negative 3. What's our fail to reject decision? Rejected. Yes, it is past the critical value of negative 2.33. So we know we're going to reject it, but just for fun, let's figure out the p-value. P-value. All right. This will tell us how much further past the critical value it actually was. So to find the p-value, we look at the area under the curve associated with negative 3. And we will find it separates the bottom, fraction of 1% of data from everything else. What do we see in the area under the curve when we look at negative 3? 0.0013. Okay, so that's about 1/10 of 1%. Do we have to double this? We do not have to double it because we're only looking at one tail. There was only one way we could reject this null hypothesis. Okay? Questions?
I'm just still a little confused with this.
The z?
Yeah.
The 2.3?
Yeah.
Okay. All right. Can somebody explain this negative 2.3 for us? Somebody just take a shot, and that'll give me a little perspective, and then I'll jump in and we'll make sure Diane and everyone understands. Okay, fine. All right. So the question is, how do we get this negative 2.33 z value, right? All right. Well, we decided when we started this decision process that what we consider to be acceptable unlikely, 1%. All right, if it's less likely than 1%, then we're going to say, I reject your null hypothesis. If it's more likely than 1%, if it's the kind of thing that happens 2% of the time, 3% of the time, we'll say, well, we're a little suspicious, but we're not going to reject. So we know that this sampling distribution of the sample mean is normally distributed. So we know how much data is in every part under this curve. That's the beauty of the z-table. Because we know this is normally distributed, we can calculate how much percentage of the data is within 1 standard deviation of the mean, 2 standard deviations of the mean. We went through that whole thing. 2 standard deviations of the mean is going to capture 95.5% of the data. This is just a way to get at the exact number we're looking for. So what we mean by unlikely, our threshold for unlikely, is 1%. So if it happens less than 1% of the time, we're going to reject. So we want the z-value that separates the bottom 1% of the data from the top 99% of the data. That make sense, Lauren? So we want the z-value that separates the bottom 1% of the data from the top 99% of the data. And if it falls in that 1% range, then we're going to say, that is so unlikely we don't believe that what you're saying is true, we're going to reject. All right, so the question is, what is the z-value associated with the bottom 1% of the data? We look on the table, and we see that it's negative 2.33. Any questions? All right, let's go through these slides really quick. And the great thing about the slides at this point is there's nothing new. It's just a way to summarize the data and, or not the data, summarize the material. All right, so today we talked about statistical hypothesis testing, and we talked about using a population mean for this hypothesis testing. And just preview of next week, or the video for next week, all we're going to do is we're going to add the usual suspects. Testing for a proportion, testing for a mean difference, and testing for a population or proportion difference. So we're just going to add those components. We're going to have a couple new formulas, or one new formula pretty much for each, and we're going to use the same thought process. We talked about the nature, we talked about establishing the hypothesis, we talked about one-tailed tests, two-tailed tests, and then lastly we talked about using the t-distribution if we don't know the population mean. So, let's see. In the hypothesis testing, a statement called the hypothesis is made about some characteristic. Then we take a sample to establish whether or not we think that statement is true. If the sample results would be unusual or highly unlikely, Then we conclude the statement's false and we reject it. Null hypothesis is denoted with the HO. Alternative hypothesis is denoted with the H with the little a. All right, so the status quo position serves as the null hypothesis. So again, we need compelling evidence to reject the null hypothesis. Something that is only 10% likely, only 5% likely, only 1% likely. You could choose any significance level, but we need compelling evidence, and we decide before we start the test what we mean by compelling evidence. All right, so we could look at the mean is greater than some number. The realtor might have told us that the mean is less than some number, or the realtor might have told us that the mean is equal to some number. And the alternative hypothesis would just be the opposite of that. Note that the two-tailed tests are when we're saying something is equal to a certain number. And we could make a mistake, or not make a mistake, we could disprove that one of two ways. That means we need a two-tailed test. One-tailed test, we only disprove it one way. And if I'm going too fast, stop me and ask me questions, but I don't want you to think that I'm teaching you anything new. I'm just trying to summarize quickly. All right, so we went through a process with our, say, one-tailed test. The sampling distribution of the sample mean is key to making our decisions, because we know if we take samples, it goes on that beautifully normally distributed sample mean, the sampling distribution of the sample mean, and then we can say, well, that's only 5% likely or 1% likely because of what we know about the sampling distribution of the sample mean. We choose our significance level, we compute various things, we apply the decision, and then we calculate a p-value if we so choose. Let's see, sampling distribution of the sample mean, you know this already, seen it. Choosing a significance level. All right, let's go straight to the definition of our significance level. Is the probability value that defines just what we mean by unlikely sample results under an assumption that the null hypothesis is true. Significance level is what do we mean by unlikely, our threshold for unlikely. Then we establish a decision rule, which is just basically what we call critical values. In the first example we did after break, we said negative 1.96, positive 1.96, those are our critical values. And if the test statistic is outside those critical values, we reject. And that was the question me and Diana and Lauren got into with what's the negative 2.33. Well, that's the critical value. That's the point where it crosses into that's so unlikely that we're going to reject what you say. Okay. All right, so we reject decision rule. This is all talking about a one-tailed test. And then we calculate the test statistic, which is how many standard deviations our sample mean that we calculated is above or below the assumed true population mean. And if it is more extreme, our test statistic is more extreme, then we reject the null hypothesis. All right, we've got a nice little chart we can look at for one-tailed test. Remember, a one-tailed test just has a rejection region in one side of the tail, and if we get any data above that, we do not reject. All right, it could be upper tail, could be lower tail, depending on how the question is posed. All right, so computing the test statistic. So the realtor said 1560. That's what she or he proposed, but we went out and we did some sampling data of our own, and we got a different sample mean. The test statistic for what we got is our sample mean minus the assumed sample mean, assuming what the realtor says is true, divided by the standard deviation of the sampling distribution of the sample mean. And as we know, the standard deviation of the sampling distribution of the sample mean is the population mean divided by the square root of n. Okay. Okay, so this talks about accepting versus failing to reject the null hypothesis. I don't know if you may have just been thinking about other things when I said this as we were leaving for the break. I said that if we have compelling evidence to reject the null hypothesis, then we say we accept the alternative hypothesis. But if we don't have compelling evidence to reject the null hypothesis, we don't like to say we accept the null. Right? We don't say that the realtor was definitely telling us the truth. We just say we don't have overwhelming evidence to the contrary. And the textbook gives us this example. For example, failing to convict a defendant doesn't necessarily mean the jury believes the defendant is innocent. It simply means that in the jury's judgment, there's not strong enough evidence to convince them to reject that possibility. Make sense? All right. P-value, you've got a definition for p-value. When you're reviewing this material, measures the probability that if the null hypothesis is true, we would randomly produce a sample result at least as unlikely as the sample result that we actually produce. So this gives us an exact measure of how unlikely our test statistic would be. We might already know whether or not it crosses the significance level, but we want a more exact decision or exact information. So we look in the back of the book under Z tables, and we can find the exact probability of that happening with our p-value. Okay, this is generalizing the test procedure. You can state the null and alternative, choose the test statistic, meaning you're going to use the Z or the T, and the significance level, you're going to use 10% significance, 5% significance level, 1%. Compute the value of your test statistic, and apply the appropriate decision rule and make your decision. And we talked about how the critical value version will give us the same answer as the p-value version. The critical value is this negative 1.96, positive 1.96, or it could be different depending on what our significance level is. The p-value is the exact probability, and if the p-value is less than the significance level, like meaning it's more unlikely, then we reject as well. So it could be, if we're going to reject something, then it will be two things. It will be past the critical value on one side or the other, and the p-value of our statistic will be less than the significance level that we chose. Say, all right, it's only 2% likely to happen, our significance level is 5%, we reject. We talked about type 1 error. This is rejecting a true null hypothesis. We storm into that realtor's office and we say, what you said was wrong. Well, the realtor, if he or she took statistics, might say, well, this happens 5% of the time. This happens 1% of the time. You need to look on the extreme edges of the tail. So we could be wrong, whatever we choose as our significance level. Our significance level measures the maximum probability of making a type 1 error. Type 2 error, we can't really determine the probability of making a type 2 error. It's unknown. Right, was that realtor may have been lying to us. I just have this sneaking feeling she was, but I don't know the probability of accepting her data, the probability of us being wrong if we accept her data. All right, so two-tailed tests. Two-tailed tests start with an equality. The mean is equal to some amount. And the alternative is, of course, the mean is not equal to the amount. So we could disprove the null hypothesis two ways, with an extremely high test statistic or an extremely low test statistic. So when we're calculating the critical values, we take the significance level divided by 2, put half of it in the upper tail, half of it in the lower tail. We calculate the test statistic as the difference between our means divided by the standard deviation of the sampling distribution and sample mean. And then remember, the p-value for a two-tailed test needs to be doubled once we look in the back of the book. Okay, so two-tailed test, we're going to have our critical value, which would be a z-value, right, depending on the significance level, and that's how it would break down. Okay, two-tailed test, form a hypothesis, conduct a two-tailed test of the population mean simply by constructing. Okay, this is the first thing we did. Remember, I started off class by constructing a confidence interval. I said that if what the realtor says is true, that the average rent is $1,560, what would we get for our sample means 90% of the time when we test for sample mean? And we crunched it out. It was like between 1543 and 1586. And that's the way we've done confidence intervals up until now. And this hypothesis testing is using that exact same type of math. It's just looking at it a different way. It's not just to annoy you, it's to think about how scientists make these types of decisions. How scientists are methodical about supporting their decisions and understanding what assumptions they're making, understanding what type of error they could be making, and the probability associated with those. Okay, now, if we do not know the population standard deviation, we need to make two changes. And those are, one, sample standard deviation, which is going to be a little bit bigger. I don't think you'll ever have to calculate it in this class, but you'll know how to calculate it on Excel if you need to. The other thing we need to do is use the t-distribution, which is going to be a little bit shorter and fatter than the z-distribution. It's going to give us a wider interval to account for the unknown factors. Okay. We can do one-tailed, two-tailed, same thing with t. P-values, we could calculate p-values with the t-distribution, but because the chart in the back of the book doesn't give you a lot of information, you would either just have to estimate based on what it says in the back of the book, or you could use Excel for an exact p-value. There's definitely no quiz questions where you have to get a p-value for a t-distribution, but you just may want to realize that or be cognizant of that, because if you do this in the real world, you'll just have to get the exact number from Excel. End of slideshow. All right, applause, please. Just kidding. That was a joke. Okay, so, like I said, I will be here next week. I'd recommend you come, and it'll be a good chance to go over questions, go over Excel. You're used to coming on Mondays anyway, so you get a bonus. You get a video, which will just be pretty straightforward information, and then we could work together next week. And also, if you can't make it next week, I'm always available. I'm here Mondays and Thursdays, and I'm here other times too. If you have any questions, you can email me. We can set up a time. And that's all I have. If you have questions, feel free to stay and ask them.
I get the female. For the Z, to get the Z score, to get the critical value, I don't know why with the significance level, I'm getting so caught up on this. So if it's a 5%, do I just do 1 -0.05 and work up that value in the back of the book? Because that's how the
If
book
we're one-tailed test, yeah.
That's how that's only for one test. So
With 2, you can divide the critical value by the significance level by 2. Sorry. I know it's tough. Maybe I know.
that's why I was like, why is this working with some questions and not others? I was so confused.
Oh my gosh. Well, this is good. This is good. You've thought through that process, and you've obviously got it. Now you've made that discovery. It means you're thinking critically. Sonny, do you want to talk about z-tables?
Z-tables, yes.
Let's do it.
Wait,
Let me get the lights. What?
We're confused about getting the value of the critical value.
Okay. Well, let's start with an easy one for sure.
After looking at the Z table, getting different triggers at other people in the class.
Okay. Oh.